We are going to look at intermolecular forces now. Intermolecular forces are the forces between molecules in solids and liquid phase, and we're going to identify them and then use this knowledge of the types of forces and relative strengths of forces to predict relative levels of some physical and chemical properties. So intermolecular forces are attractive forces that occur between particles, molecules, ions, in the condensed phase, which means solids and liquids. It is negligible in the gas phase. When it occurs in the gas phase, then we have a non-ideal gas. So if we're talking about forces within one substance, they are called cohesive forces. If we're looking at the forces between two different substances, they would be called adhesive forces. So the forces within water that holds water together would be a cohesive force. The force that draws water up a glass tube, so that's the attractive force between the water and the glass, that would be an adhesive force. These forces are going to show up in a number of physical properties such as boiling points, melting points, viscosity. So we're going to look at some of these forces and look at how they affect some physical properties. So for covalent molecules, molecules made up of non-metal with non-metal, we can have either polar or non-polar molecule. A polar molecule means that there's a permanent charge separation. So in water, which is has a special case, we'll talk about that, a special case of polar, the oxygen is more electronegative than the hydrogen. So the oxygen pulls the electrons across this bond. So the electrons spend more time around the oxygen than they do around the hydrogen. So that makes the oxygen partially negative and the hydrogen is partially positive. We can see this in an electrostatic potential map where the red represents negative and the blue represents positive. So there's a charge on the surface of the molecule. A dipole, polar molecule, a dipole, so it has two poles, a positive pole and a negative pole. And we're going to see this whenever we have an electronegativity difference between the atoms of 0.4 or greater. Nonpolar molecules occur for two reasons. Nonpolar molecule will occur if the electronegativity difference is 0.4 or less, is less than 0.4. Then all the bonds are nonpolar and we have a nonpolar molecule. We're also going to have a nonpolar molecule if we have a polar bond but a highly symmetric molecule. A highly symmetric molecule occurs when the poles across the bonds balance out. And this will occur in a couple symmetric situations, such as carbon dioxide, where we have a linear molecule, oxygens on both ends, carbon in the center. The oxygens are pulling equally against each other. It's a tug of war that no one wins. And in that, you'll see that the carbon dioxide has there's no lone pair on the carbon of the carbon dioxide. We can have a trigonal planar molecule like sulfur trioxide. Now we have oxygen being pulled in three different directions, but it's a perfect triangle, so these three directions balance each other off, creating again a nonpolar, a three-way tug of war that does not have a winner. So it ends up being a nonpolar molecule. And again, the sulfur in the sulfur trioxide has no lone pair on it. Or we can have carbon tetrafluoride, so 4 fluorines on carbon. So the fluorines are pulling in a tetrahedral geometry, and that tetrahedral geometry is highly symmetric, giving us a 4-way tug of war with no winner. So it also is a nonpolar molecule, even though the bond the electronegativity difference between carbon and fluorine creates a polar bond. And again, there's no lone pair on that central carbon. That's a common feature for symmetric molecules that obey the octet rule. For solutions, when we dissolve ionic compounds into water or other polar solvents, like alcohol, the water or alcohol has a dipole to it. The ionic compound consists of positive and negative ions, and when the ionic compound dissolves, those ions separate into solution. So what is helping the ions to enter the solution is the attractive force between the ion and the dipole of the water molecule. And the dipole will switch depending on which ion is being solvated. So sodium ion will be surrounded by the negative oxygen side of the water. The negative chloride ion will be surrounded by the positive hydrogen side of water. So the ion dipole attractive forces are forces for solutions, for ionic compounds in solutions. So for molecular compounds, solids or liquids, we're dealing with covalent compounds containing only nonmetals. The composite unit is a molecule. We're going to have three types of intermolecular forces that we're dealing with. The strongest of them would be hydrogen bonding. This is a special case of dipole-dipole. So dipole-dipole bonding is when we have polar molecules. They'll line up with the opposite charges next to each other to create an attractive force. And dispersion forces are always present, but they are the predominant force when we have a non-polar molecule. So hydrogen bonding, this is a special case of dipole-dipole. It only occurs when we have hydrogen directly attached onto nitrogen, oxygen, fluorine. We can see this in terms of physical properties. So for boiling point and melting point of a column from the periodic table, oxygen, sulfur, selenium, tellurium. We add hydrogen on that to get water, hydrogen sulfide, and so forth. If we ignore the water one, just look at H2S, H2SC, H2TE, the melting point and boiling points increase as we're going down the periodic table as we get into bigger molecules. This is a property of the dispersion force. The dispersion forces increase with molecular mass. So as we increase the molecular mass, we're increasing the attractive dispersion force, which is holding these substances as solids or liquids. So the stronger the force, the more it holds the solid and the liquid together. But we have this strange case where the lightest one, water, has the highest melting point and the highest boiling point. Why does this happen? This is a combination of two factors. These elements, nitrogen, oxygen, fluorine, are three of the most electronegative elements that we have, along with being the three of the smallest elements that we have. So we're going to have a high charge separation under a short distance. This high charge separation under a short distance creates an extremely strong dipole-dipole interaction, strong enough that it behaves differently than other dipole-dipole interactions, so we give it a special name of hydrogen bonding. So hydrogen bonding occurs only when you have hydrogen directly attached onto nitrogen, oxygen, fluorine. And we can see this in this other chart here where we have additional groups. So in addition to the oxygen group, we have the halogens, the nitrogen group, and the carbon group. So the carbon group behaves with no hydrogen bonding. So methane has the lowest boiling point, silane is higher, GH4 is higher, tin 4 hydride is higher. So the carbon shows no special attractive force, but the nitrogen, the fluorine, and the oxygen do. So these three elements alone, they show a tremendous increase in boiling points, melting points, and other attractive forces. So when we have hydrogen directly onto the oxygen, hydrogen, and nitrogen, that's a special case of dipole-dipole called hydrogen bonding. We can compare different molecules with and without hydrogen bonding. So using similar compounds, 3-carbon chain compound, acetone, which is a carbon double bonded with oxygen. So this will have a polar bond to it. Or isopropyl alcohol, where the central carbon has an OH group on it. So now we have hydrogen directly onto the oxygen. So we compare the melting point and boiling points of these two. The melting point and boiling point are lower for the acetone. So the dipole-dipole is weaker than the hydrogen bonding. Hydrogen bonding is stronger. So the hydrogen bonding holds it as a solid until a higher temperature and holds it as a liquid to a higher temperature. This is the electrostatic potential map of water, again, where we have the negative side of oxygen and the positive side of hydrogen. Dipole-dipoles, the attractive force there comes from the fact that the molecules have a permanent positive side and a permanent negative side. So the molecules will do their best in solids and liquids to arrange themselves so the positive side of one is adjacent to the negative side of the other. And it'll try to do as many of those combinations as possible in the three-dimensional liquid or solid. So when we have a permanent dipole, permanent charge separation, a polar molecule, this creates an electrostatic attraction between the molecules in both the solid and the liquid phases. So this helps hold the solid as a solid and helps to hold the liquid as a liquid. So a comparison of dipoles here. So again, we're taking this a 3-carbon backbone here. On isobutane, we have a methyl group, CH3 group, on the central carbon. This will be a nonpolar molecule. So there's no charge separation at all in this molecule. Or we can have a chlorine on that central carbon. This will give us a dipole, but it's not an overly strong dipole. Or we can have that double bonded oxygen on the central carbon, and that'll give us a strong dipole. So we look at the melting points, and isobutane has the smallest melting point at minus 137. Isopropyl chloride has minus 117, this is a higher melting point, and acetone minus 94, a higher melting point. So the stronger the intermolecular force, the higher the melting point, the more it's held as a solid. Same for liquids, the boiling point for isobutane is 0. Boiling point for isopropyl chloride is 35 degrees Celsius, and for acetone is 56 degrees Celsius. So the stronger the intermolecular force, the higher the boiling point, the more it's held together as a liquid.